This is the last section of this chapter on discrete probability distribution, and not only that, it is a section that only HL needs to know about. So this is the only other discrete probability that HL needs to know about. SL only needs to know about binomial. This one is called the Poisson distribution. It's named after the guy that either discovered it or did experiments with it, figured out the formula, whatever he did. His name was Poisson, and I don't even know his first name, but he's the guy that figured this thing out. So let's talk about what this is. First of all, let's figure out when we know we have a Poisson distribution as opposed to binomial. There is not a set number of trials like there was with binomial. Instead, all we know is the expected number of successes within a certain fixed distance or time or something that is like a fixed quantity. And we know how many times we can expect something to happen within that fixed quantity. Kind of a vague concept until you see some examples and see how it's different from binomial distribution. But what we're going to do is we're going to call mu the expected number of successes in a fixed interval. And so we're going to figure out the probability of being successful x times. Now here's the formula. I'm giving you the formula first because it's really complicated to figure out where it comes from. You need to know a lot about sequences and series, that part of calculus that we don't need to know. You might want to look up where this formula comes from, but as far as needing to know how to derive it, you don't need to know that. You only need to know how to use it. So there it is. It is given to you on your formula chart. So let's go through some examples of how to use it. I'm driving for 10 miles and I pass 14 gas stations. So I need to know what's the probability that in the next 10 miles I pass exactly 12. So if I look at what my variables are, my expected number of gas stations that I'm going to pass is 14, and I want to know what the probability is that I only pass 12, so my x is 12. If I plug those into the formula, that's what it looks like, e to the negative 14 times 14 to the 12 all over 12 factorial, and that works out to be 0.0905. So not a real high probability, like 9%, that you're only going to pass 12 gas stations in the next 10 miles. But that is making a huge assumption that I'm only passing 14 in the first 10 miles, and I'm assuming that that's going to happen every 10 miles. Kind of a big assumption there too, but we're just looking at the theory of this. So now I'm going to change things up a little bit, and I'm changing the distance that I'm traveling. So I want to know the probability that I pass exactly 8 gas stations in the next 5 miles. What that's going to do is that's going to change my mu, because my mu of 14 depended on the fact that I was driving 10 miles. Well, now that I'm only driving 5 miles, I need to adjust the number of gas stations that I can expect to see, and that's going to be 7. And my x will stay as 8 because that's also dealing with a 5-mile distance. I plug those into the exact same formula, e to the negative 7 times 7 to the 8 all over 8 factorial, and I get 0.13. So that's how you use the formula in those examples. Now let's talk about, just like we did with binomial, let's talk about what the values of Ex and var x are going to be, basically the mean and the variance of this distribution. It's actually the easiest one to remember because those are both mu. Expected value and variance are both mu in this distribution. Just like with binomial, you have some calculator functions in your catalog as far as the Casio goes. Both PD, probability distribution, and CD, which is more cumulative, they only need 2 inputs, x and mu. So x being the number of times you want to be successful, and mu being the expected number of times that you will be successful. So that's all you really need to plug into the calculator to do this by calculator. That's it for this lesson. That's it for this chapter. And if you have any questions, let me know, and I'll see you tomorrow.